Good day everyone, I am Jessa Guipo and I am the second reporter about the chapter 5 entitled gases. And today I'm gonna tackle about the ideal gas law, the gas stiochoimetry, and the Dalton's law partial pressure. So the ideal gas law. The ideal gas law mathematically relates the pressure, the volume, the amount, and the temperature of the gas with the equation of pressure times volume is equal to moles times ideal gas times temperature. Or can be written in empirical form, which is PV is equal to nRT. The ideal gas law is ideal because it ignores interactions between the gas particles in order to simplify the equation. Because in ideal gas, there is no intermolecular attraction between the molecules of an ideal gas. So, PV is equal to nRT is the formula of ideal gas, whereas P is the pressure and the unit of pressure is atm. And the V is the volume and the unit of the volume is the liters or liter. And N is the number of substance. Its unit is mole. The R is the ideal gas constant. And the temperature, T is the temperature, is the unit of temperature is Kelvin. The ideal gas constant, its value is 0.08206 with a unit of liter per atom over mole per Kelvin. So, and the constant value of the Kelvin is 273.15 Kelvin. So, we try this example. An automobile tire at 23 degrees Celsius with an internal volume of 25.0 liter is filled with air to a total pressure of 3.18 atm. So, determine the number of moles of air in the tire. So, in this problem, it's asking for the number of moles in a tire. So, before we solve or to go on the solution of the problem, we first list down the given. So, our given is the pressure, which is 3.18 atm, our volume, 25.0 liter, and the temperature, which is 23 degrees Celsius. And the constant ideal gas, which is 0.08206 liter per atom over mole per Kelvin. So, we're looking for the number of moles. So, the formula is PV is equal to nRT. So, to get the number of moles, we derive it. So, PV is equal to nRT. We divide both sides by RT, and also here to get the number of moles. So, N is equal to PV over RT. So, this is now our formula to get the number of moles. So N is equal to PV over RT. This is our formula now. So, we substitute the value. So, our P, which is our pressure, is 13.18 atm. Our volume is 25.0 liters. And our constant ideal gas is 0.08206 liter per atom over mole per Kelvin. Yes, and then we cannot proceed in the value of our T, which is the temperature, because the international system unit of the temperature, which is Kelvin. So, the constant value of Kelvin is 273.15 Kelvin. So, to proceed our equation, we derive it our given, because our given in this problem is 23 degrees Celsius. So, to get the total value of our Kelvin, so we add the constant value of temperature to 23 degrees Celsius. So, it come up 296.15 Kelvin. So, and substitute the value here. In our formula, the temperature is 200 96.15 Kelvin. So multiply the 3.18 atom and 25.0 letters. So it come up 79.5 letters, and also here the 0.08206 and the 296.15 Kelvin multiply. Its result 24.29 rather. And then cancel out the same unit, atoms and atoms. The same here also the letters or letter, and then the Kelvin also here. So the remaining unit is the mole. So our unit here is a mole. So we divide 79.5 to 24.29. It come up 3.27 mole. So now the number of moles in a tire is 3.27 mole. So we proceed. The another example. What is the pressure in 304.0 liter tank that contains 5.670 kg of helium at 25 degrees Celsius? So in this problem, it looking or it asking the value of the temperature. So first we write down our given. So because we're looking for P, so the P here is the unknown. So V, the value of the volume or the V is 304.0 liters, and the N, the given is the number of moles, which is 5.670 kilogram. The constant ideal gas, the 0.08206 liter for atoms over mole per Kelvin, and our temperature is 25 degrees Celsius. So here the formula. So to get the formula in getting pressure, so we convert it. So we have Pb is equal to nRT, divide both sides by B to get the P. So P is equal to nRT over B. So this is now our formula. In getting the number or the pressure. So we know that the unit of temperature here is the Kelvin. So we derive it. So we have 273.15 Kelvin plus 25 degrees Celsius. Degree Celsius, it come up 298.15 Kelvin. So this is now the value of our temperature. But we know, and also in ideal gas, the unit of the number of mole is mole, but here in the given is kilogram. So we convert it into a mole. So first the kilogram, because in the number of moles is equal, the equation of the getting the number of mole is mass over the molar mass. So we know that the unit of mass is grams. So but here is kilogram. So we convert it into grams. So 5.670 kilogram to gram multiply by 1,000. So in 1 kilogram, it have 1,000 gram. So 5.67 kilogram multiply by 1,000 grams and divide by 1 kilogram. So it come up 5,670 grams. So this is now our mass. So wait lang. So here our mass is 5,670 grams. So the number of moles is 5. Our mass is 55670 grams. Then the molar mass of helium, because in the problem And the problem here is the helium. So, asking for the 5 kilogram of helium. So, in the periodic table, the molar mass of the helium is 4. So it's 4 grams per moles in the periodic table. So, 5,670 grams divided by 4 grams per mole. So, it come up 1,417.5 mole because cancel out the grams. So, the mole is the remaining. So, the unit of this is mole. So, now we'll already get the value of our moles, which is 1417.5 mole. So, we proceed the equation. So, PB is equal to nRT over B. So, P, our number of our is equal to N. So, our moles is 1,417.5 moles. And the constant ideal gas is 0.08206 liter per atom over mole per Kelvin. And our value of our temperature is 298.15 Kelvin. And the value of our volume is 304.0 liters. So, multiply this, the 1,417.5 to 0.08206 and 298.15. So, it come up 34,680.82 atm because the mole is the cancel out because it's same unit, and also the Kelvin. So, the remaining is atm. So, atm. So, cancel out the liter also because it's same unit. And 34,680.82 atm divided by 304.0. So, it come up 114.8 atm. So, this is now the value of our pressure. So, in this problem, the pressure in the tank that contains of 5.70 kilogram of helium is 114.02 atm. So now we proceed to the gas stiochoimetry. The stiochoimetry is the quantitative study of the relative amounts of reactants and products in chemical reactions. Gas stiochoimetry involves chemical reactions that produce gases. And the gas stiochoimetry is based on the law of conservation of mass, meaning that the mass of the reactants must be equal to the mass of the products. So we have here the molar volume of an ideal gas, which is the STP. STP means standard temperature and pressure, which is the value of this standard temperature, which or ST is 273.15 Kelvin, and the value of our standard pressure or SP is 1 atm. This is the constant value. And we proceed this example. 1 mole of an ideal gas is 0 degrees Celsius and 1 atm. What is the volume of the gas? So in this problem, it's asking the volume of the gas. So first we write down our given. So the pressure, we have 1 atm. The constant ideal gas, 0.08206 liter per atom over mole per Kelvin. And the number of mole, which is 1 mole. And the temperature, the value of the temperature, the constant value is 273.15 Kelvin. So the formula of ideal gas is this: PV is equal to nRT. So because we're asking for the volume, the value of the volume, so we derive the formula. So we derive the formula. So PB is equal to nRT, divide both sides by P to get the V. So V is equal to nRT over P. This is now our formula on getting the volume. So we substitute the value. We have the number of mole, which is 1 mole. The number of the constant ideal gas is 0.08206 liter per atom over mole per Kelvin. And the value of our temperature, which is 273.15 Kelvin. And the value of our P is, the value of our P here is 1 atm. So, multiply 1 mole to 0.08206 and to 273.15 Kelvin. Divide by 1 atm. So, it results 22.42 liters. So, in this problem, the volume of the gas is equal to 22.42 liters. So we proceed to molar mass of a gas. Molar mass is the mass of a given substance divided by the amount of that substance measured by gram in a mole. So the unit of the molar mass is gram per mole. So this is the formula on how to get the molar mass, which is molar mass is equal to d RT over P, whereas the D is the density of the gas, the T is the temperature in Kelvin, the P is pressure of gas, and R the universal gas constant. So we try this example. What is the density of fluorine at STP in gram per liter? So in this example, we asking the density of fluorine at the STP in the gram per liter. So before we proceed, we write down first our given. So our given is the ideal gas constant with 0.08206 liter per atom and mole per Kelvin. And our temperature, the constant temperature, is 273 Kelvin. And also our molar mass, the fluorine. So, in a periodic table, the value of fluorine is 18.99 something, but we round off it. If we round off, it come up with 19. So, because here in the given is F2, so we multiply by 2. So the result is, so it results 38 gram per mole. This is gram per mole. Sorry for the error. It's gram per mole. So 38 gram per mole is the value of our molar mass. So the equation of the molar mass is M is equal to dRT over P. So because we're looking for the density, we convert the equation. So M is equal to dRT over P. So we here they have 1, so we put here a 1. So when multiply 1 to dRT. So dRT is equal to multiply P into M, so it is PM. So divide both sides by RT to get the formula. Also here RT, so D is equal to PM over RT. So this is now our formula on getting the density. So we substitute the value. So the value of pressure or P is 1 atm. The value of our molar mass is 38 gram per mole. This gram per mole. Then over the constant ideal gas is 0.08206 liter per atm over mole per Kelvin. And also the value of our temperature is 273.15 Kelvin or 273 Kelvin is the constant. So here is 1 atm multiplied by 3 gram per mole. Here, gram per mole, so it come up 38 gram. Because 38 gram. And then, here, here, so we have 0.08206, you multiply in 273.15 Kelvin, so it come up of 22.41 liters. So, because gram here, so because ATM we cancel out the same unit. So, ATM here and also here, so we cancel out that both ATM and also the Kelvin and the mole. So, the remaining unit is the gram here and the liter. So, the density, the result is 1.70 gram per liter. This is now the density. So, the density of the fluorine at STP in gram per liter is 1.70 gram per liter, rather 1.70. So this is the density of fluorine. So let's proceed to Dalton's law of partial pressure. According to Dalton's law of partial pressures, the total pressure by the mixture of gases is equal to the sum of the pressure of each of the constituent gases. The partial pressure is defined as the pressure each gas would exert if they alone occupied the volume that mixture at the same temperature. So, we try this example. 27.4 liters of oxygen gas at 25.0 degrees Celsius and 1.30 atm, and 8.50 liters of helium gas at 25.0 degrees Celsius and 2.00 atm were pumped into a tank with a volume of 5.81 liters at 25 degrees Celsius. Here the question. So, the problem is calculate the new partial pressures of oxygen. So, we calculate the new partial pressure of oxygen. So, first, for that, the second question is calculate the new partial pressure of helium and calculate the new partial pressure of both gases. So, before that, we first write down our given. So, here in the problem, so the given is here the oxygen gas. So, the 27.4 liters. So, this is the value of the volume. So, given is the volume. So, given is the value of the volume and the value of the temperature, which is 25.0 degrees Celsius, and also the value of our pressure, which is 1.30 atm. This is only for oxygen gas, and also here the value of our B2 or pressure, volume 2, which is 5.81. So PV, the formula of this in getting the pressure is PV P1 multiplied by B2 is equal to P2 multiplied by B2. So our given is our P1 is 1.30 atm because we're looking for P2, so our P2 here is unknown. So our value of our B1 or volume 1 is 27.4 liters, and the value of our volume 2 is 5.81 liters. So, because we're looking for the P2, yes, but the P2, we're looking for the P2, so we derive the equation. So, we divide both sides by B2 to get the P2. So, we have P2 is equal to B1 multiplied by P1 multiplied by B1 over B2. So, this is now our formula on getting the new partial pressure. So, in substitute the value, so we have P1 or the pressure 1, or our P1 is 1.30 atm. Our B1, the volume 1 is 27.4 liters. And then our volume 2, our B2 is 5.81 liters. So cancel out the letters, the same unit here. So in 1.30 ETM to 20 multiplied by 27.4 liters is come up with 35.62 ETM, and because they cancel out the same unit, so the remaining is ETM. So we have 5.81. So 35.62 ETM divided by 5.81, it result or come up with 6.13 ATM. So the new partial pressure on the oxygen gas is 6.13 ATM. So here in the helium, because in the second question here, so here, okay, in this, the new partial pressure of oxygen is, we can come up this 6.13 ATM. So the next question is calculate the new partial pressure of helium. So the given is 2.00 ATM ang P1. So and then ang the B2 is 8.50 liters, and the B1 is 8.50 liters, and the B2 is 5.81 liters. And we're looking again the P2, the new partial pressure. So still this the equation formula we gonna use. So we have 2.00 ATM multiplied by 8.50 liters, and our B2 is 5.81 liters. So we have 2.00 ATM multiplied by 8.50 divided by 5.81 liters. So it come up 293 ATM. So the new partial pressure of helium is 293 ATM. Calculate the new total pressure of both gases. These two gases. So in the both gases, we just add the value of our the value of the oxygen, the new partial of oxygen, which is 6.13 ATM, plus the new partial of helium, which is 2.93 ATM, that result 9.06 ATM. So here the total pressure of both gases is 9.06 ATM. Okay, and that's all. Thank you, and God bless everyone.